Is it on? I guess for the purposes of the film, Becca 1, review tolerancy in chapter 17. So then we're into the bilateral, which is this method shown here. Again, it's a direct tolerancing technique. Here we give the basic size, so the size we want the part, and then we give the deviation from it. Maybe you can go plus plus, you can go minus minus, you can do plus minus, you can do 0 minus, or plus 0. Any of those techniques work. All right, that's kind of my review of tolerancy. Keep in mind, every part needs a tolerance. Why does it need a tolerance? Because we can't build to perfect size. Can we design to perfect size? Yeah, we have capabilities in here to be virtually perfect, don't we? And we can go to 9 decimal places, which is way past what we can build to. So you want to kind of pay attention to that. Yes, sure.
I know in general when you're giving number measurements, you drop the 0 before the decimal point. And on these tolerancing, isn't that a general rule that we follow?
Yes, on English units, we don't give leading zeros. On metric units, we do.
Oh, okay, so these must be metrics.
Yeah, this is a metric deal.
Oh, yes.
Yes, Dave.
So with the bilaterally tolerant stuff, you said there could be like plus plus and minus minus. So what would that be? Like how would they change what the number actually was starting with? So that would be a plus minus.
It gets into mating parts. Remember when we did fits where you had a clearance fit, a transitional fit, and a friction fit? Those 3? And we based them both off of a basic size. So if we had a cylinder and a hole, right, we can design both of those based off of, let's say, 3/4. And then we would dimension the cylinder that's going to fit in the hole as 3/4 minus minus, because it's got to be smaller than 3/4. Then we would take the hole and dimension it as 3/4, and we might say a 0, so 3/4 and a plus. So that it's bigger. That way we ensure that those 2 mating parts fit together. Okay, that's the only time you really see that is when you're using our fits. Now, I wasn't really planning on going over that, but that picks up right here in these next couple chapters. And we did a worksheet on this back in the day. And this is going to come up a little bit. So if you look at 847, okay, there's this little chart right here that kind of explains fits and how we do it. And in essence, we're trying not to reinvent the wheel here. All this is documented in the Machinery's Handbook. In fact, you have some in your appendix on this, so that if you get a situation where I'm going to put, some pin into some hole to hold some device, depending on how I want it to work, I can get all of that dimensions without building the part and putting it under stress and seeing how it works. Because that's pretty expensive to kind of run into a prototype lab and pay somebody to figure all that out for us. Did that answer your question okay?
Yeah.
All right, any other questions on tolerancy? Okay. Now we're going to geometric dimensioning and tolerancy. Remember, what we're trying to do here is to target specific items and how they work. Now, I don't know that the author gives a great, that's kind of why I copied the handout, because I just don't really think that the visual in here is that great. But let's start with this picture, figure 18.1, and kind of get an idea of what we're talking about. So here they have a tabletop, looks like to me. Okay. Now they've gone and said, okay, I want this tabletop to be 30 millimeters plus or minus 1 millimeter. Okay, so we know from this surface to the top here, I have to be 31, 30, or 29 millimeters, measuring that dimension. That's a size tolerance. Now, when you create this, though, and we cut this across, Can we cut it perfect to that? No, we can't. In essence, what the tabletop's going to end up looking like, you take this little circle and you come down here, and it's going to have these little waves in it. It's just going to. The blade's going to leave it. Even if you're using a laser, you're going to have different elements in there that create, it's just not going to be perfect. Can't be straight. In fact, if you reach down and you kind of feel your tabletop, that's floor mica, which is a fairly straight surface, but you can feel the roughness in it. And you just kind of feel it in your fingertips. Now, if you look at that under a microscope, it's going to look something like this, where you have those imperfect things in it. Now, so what they then did is that they came in and said, you know what, I'm going to do some GDT on that, and that's what this is the GDT box. This symbol means flatness. Okay, so we're going to check the flatness of this top, and it has to go 0.5, so 1/2 millimeter. So what we'll then do is we'll come and measure that top, and the whole top across the entire thing can't deviate more than 1/2 millimeter. So we'll measure the high spot on it, we'll find the low spot, we'll measure them, it must be less than that 0.5. And that ensures now that we are in a 2 millimeter range here, we're going to a 1/2 inch once they start the cut. In essence, that's what it's doing. So we're focusing in on that.
So the height of the table can be anywhere from 28.5 to 31.5.
Yes, it's applied after. And this was kind of a good deal. I've got another thing on my notes I'm going to look at too. But let's say that this thing right here is cut and it is 29. Does that pass inspection? So we measure from here to this corner, it's 29. Is it good to go?
Based on that, but not my
Okay, yes it is.
Yeah.
So it's meeting our size tolerance. Now, once we know that it's 29, we then are going to take this and apply it to it. Okay. So from 29, I can then check the flatness from here and say, everything from here, it has to be from 28.5 to 29.5. The GDT is applied afterwards. Now, even though that 28.5 drops below, this still passes. So it's an additional tolerance. Now, it's a good one, though, because now we're taking the functionality of that tabletop and ensuring that it's flat. And we don't have to follow that through all these other pieces, just that one.
So all GDTs are secondary tolerance,
Yes, they're a secondary tolerance,
and we know they're GDTs based on these symbols.
based on the use of the GDT box, of which we haven't talked about yet.
Okay.
Okay? Now, we're going to have some modifiers that go with this also. But for now, let's just kind of use a cylinder here. There's a pretty good one of this in your handout that explains the same thing. So here's an example that I just sketched up of a cylinder. So if we look at the cylinder, and we've got our views, but this needs to be 1 plus or minus 0.01. So we can calculate those tolerances on those sizes. Now, they can go ahead and measure this and say we get 0.99 here, we measure here it's 0.99, but this thing can come off looking like a banana. Now, this is a fairly long device, it's 5 inches. If even though they meet the size tolerance here, so it's 0.99, it's within this tolerance, if I try and slip this long thing into a hole, what's going to happen to it? It's going to bind, right? Because of its banana shape. Because if I measure from here down, I'm showing 1.01, that still passes, but this thing technically could pass being measured and be outside of what it can't get in the hole, unless you use a really big hammer. So in essence, that's what we're trying to look at. So keep in mind, we'll draw it this way, we can be perfect. We can't do it in the fabrication shop to that degree. We can't do it.
You're saying that'll always happen? Or,
Oh yeah, we can always measure something like this. It will happen every time. What we want to do is control it. Now, I kind of drew it a little exaggerated, right? This is pretty small. But if you're talking metal and like car engines or jet engines, we need these types of tolerances. It's really kind of amazing, even your vehicles in today's world. I'm getting old enough now. It is amazing how they changed just in the last 15 years. We're seeing engines that have totally been refigured. That truck I'm buying, was new to me, it's 6 years old. That thing's got, I think it's about 60% of the size of my old truck, and it has 150 more horsepower. And it has much better gas mileage. You've gone, you see your oils now, you're using a 520 or a 020 in all your rigs now. Used to be 1040.
1040, 1030.
Right? Because the tolerances are getting so tight in these things, and our ability to make things is getting so much better. You can't use those big oil molecules that won't get into these small spaces. And that's why they're changing all the oils around. So it's really kind of amazing to see how these things are working. That truck blew me away when I looked at it. I mean, it's 4.7 liter. My old truck was a 6. And my old one had 300 horsepower. This guy's got 450. Okay, and gets better gas mileage just because of our ability to build to tighter tolerances. Really kind of amazing where we're coming. Got off on a little rap trail there. Anyway, all right, let's talk about GDT. Then let's look at the symbols. Now, I did put one note on here, and I want you to just make sure you make a note of this. If there is no GDT listed on a drawing, then all of your size tolerancing will be applied to GDT. That's just an assumed constant throughout the thing. Okay. Now, what that means is some firms may not even deal with it. They just kind of ignore that this is out here. But the ones that need a high degree of precision, they will. So you can make a part very expensive by not using GDT if that is part of what your firm does. When we look at GDT, what we're trying to control, not size. Okay? Size is done through a normal tolerance. We're trying to control the geometric form. Okay? Is it flat? Is it really a cylinder? There's a bunch of these. In fact, if you go to page 885, I want to make sure you're aware of these classifications. The author breaks these down. Starting on 885, do you see in the bottom left-hand corner section 18.7.5, form controls? Okay. Then they talk about straightness. Is something really straight? Line element, okay, now line element can be a center line, or it can be a profile line, the outside of an object. The axis straightness. Circularity. Now, I've turned the page here, I'm on 887, but I'm still in our form characteristics. Circularity. Is something really a circle? Okay. Those are our form ones. Now, they give you examples through there, like on circularity, page 888. Just kind of real quickly look at that one. You can kind of see how they're testing it. So here's cylinder, just like I had drawn. Here's how it's really built when you get it off of a lathe. And what we're trying to do is control this cylinder such that it falls in the right zone. Now, when we're dealing with these form ones, like flatness, circularity, straightness, these are kind of nice in that they are measured against themselves. So therefore, there's no datums that go with them. Okay? They're just individual GDTs. So they're only with that object. Okay? So that's controlling the form of an object. Now, stay there because then we have another big one called orientation right here. The placement of features is very important when we have mating parts, right? If I've got a cylinder or a peg and I'm trying to put another thing over it, they better match up, or we can't do that. So orientation has also been included in this. Now, orientation is for mating parts, so therefore it has to have a datum or something to measure from that's common between the objects. Now, these start on page 889. And if I just real quickly look through these on page 890, you have perpendicularity. Are two surfaces really perpendicular? Do they come in at 90 degrees? If we have perpendicularity, what's the other condition that we generally deal with on those? Parallelism. That's actually on the next page, I believe. They don't actually even say it, but parallelism is also.
It's on page 89.
Is it on?
Page 89.
Oh, yeah, it's the first one. Okay, thank you. So you have those two conditions. Angularity. You know, and I really haven't explained the datum thing, I don't think, and let me give you an example of that. Let's just look at one of these figures that are under orientation where we need datums. Here's a datum symbol right here. So what this is saying is this is datum A. Now, this has been attached to an extension line, but that extension line is tying to this plane. So what it's saying is that this plane right here is the datum. Okay, that's datum A. Now, if you come into your angularity that they're using on this one, there's your angle GDT symbol. There's the tolerance. And then it tells it you are measuring that angle in relationship to datum A. So it's giving you everything you need to know to check it. So this thing's got to be, this angle has got to be, what, 59.998 to 60.002.
And that's why you put the 60 degrees in a box, because it's relating to that?
Well, you don't have to put it in a box.
Okay.
They did a basic dimension here. Remember when you put a box around one, it's considered a basic dimension or theoretically perfect?
They did it down there too.
Yeah, you don't have to put them in a box, no.
Okay.
So in essence, this datum is what we're measuring from, okay?
You put angularity on a whole, on a shaft? How do you put angle on that? It's in the bottom one? Put an angle DDT on there? See where it's pointing at?
Right here? No, that's where they put the dimension. The dimension could have been pulled off of here too, but it would have gone through the object, so they just dimensioned that little part. The shaft doesn't have anything to do with it. They're talking about this plane right here.
So I'm